Consider a 2D Cartesian coordinate system. Okay, and in this coordinate system, we have two vectors defined u and v. And as you can see, as they're defined along x and y direction, they are perpendicular to each other. Okay, you can also say that the vector u and v are orthogonal to each other. Okay, so for any vectors u and v to be orthogonal, their inner product or the dot product would be equal to 0. Expanding on that, if our vectors are defined by their components, then I can write the dot product between these two vectors and the dot product would be u1 v1 plus u2 v2 is equal to 0. And this is our dot product or inner product. And the condition here satisfies the orthogonality. Okay, so similarly, if we have two functions f of x and g of x, we can define the inner product of the function as the integration over the domain on which it's defined, f of x times g of x dx. Okay, and it seems strange at this point that how do we come up with this definition for an inner product of the two functions as compared to seeing the inner product of the two vectors. Okay, so let's try to clarify this. Let's say this is our interval a and b, over which are two functions. This is f of x and g of x are defined. Okay, so now consider evaluating both the function at discrete points. Okay, so then I can write f1, f2, f3, f2, fn, similar for g, g1, g2, g3 to gn. And I can write these discretized values as a vector for each function. Similarly for g, contains values from g1, g2 all the way up to gn. Okay, and here note that the interval for the discretization is delta x. Okay, so then following the terminology from the vector multiplication, we can define the inner product of the two functions as summations, where I is varying from 1 to n, fi gi. Okay, let's be more specific about that. Here fi is nothing but f evaluated at xi, and gi is g evaluated at xi. Now, as you would notice here, if we increase the number of intervals n, for example, making it twice as dense, so increasing the number of interval will increase the value of the inner product. So we want to normalize this value. So if you also notice that as we increase the number of intervals, the size of the interval will decrease, right? So it makes sense to normalize with the size of the interval. Okay, so the normalizing with x, with delta x, we simply multiply the inner product with delta x. So then I have summation I going from 1 to n f times g times delta x. Okay, and as you can see, if n tends to infinity, that means delta x tends to 0, we can convert this term into an integral form. Okay, so from this, let's redefine the inner product as integration from interval a to b f of x times g of x dx. From this, we can define the orthogonality of the functions. Two functions f of x and g of x are orthogonal if the inner product of the two functions is 0. You have probably seen the example of orthogonality in the Fourier series. Where the function sine and cosine of x are orthogonal. In finite element analysis, though, we utilize such orthogonality to minimize the error in our solution. Such as, in next week we'll talk about Galerkin method, in which our approximate solution to the partial differential equation is orthogonal to the error of the solution.